I'm Bob Duhamel, and today I'm going to talk about alternating current circuits where we have inductors and capacitors in parallel. I've been dreading doing this video because there's one thing I cannot yet do that I do in almost all of my other videos, and that is explain why a circuit does what it does. And I have not been able to figure out a way to illustrate why inductors and capacitors in parallel do what they do. I can only tell you what they do. I can show you the mathematics to calculate what they do, but I haven't figured out a way to illustrate why they do what they do. So without further ado, let's get on with it, and hopefully I can explain the why in another video in the future. Let's start with a circuit with a sine wave generator and carry that over here to an inductor and back over to a capacitor in parallel and back over to the function generator. And to begin with, let's look at how this would react to DC. That'll help us understand why it does what it does under AC. So if we put DC across here, let's say that's a battery. Oh, it doesn't matter what the voltage is. But what's going to happen? Well, under DC conditions, the capacitor is going to look like an open circuit, and the inductor is going to look like a short circuit. Let's just pretend that this inductor is made of superconducting material under superconducting conditions, just to simplify what the circuit does. So we have an open circuit and a short circuit, which looks like that. So what do we have? We have a short circuit. So under DC, this is going to be a short circuit. All right. Now under AC, let's just assume it's a very, very high frequency. So let's get our battery out of here and put this under a very high frequency AC. So what's going to happen? The higher your frequency, the more the capacitor is going to look like a short circuit, and the more the inductor is going to look like an open circuit. So let's say it's a high enough frequency that our inductor essentially looks like an open circuit and our capacitor essentially looks like a short circuit. So at very high frequency AC, we have this, a short circuit over there. So it's a short circuit. So under DC, it's a short circuit, and under high frequency AC, it's a short circuit. So what we're interested in is, what does the circuit do in between? Well, as the frequency goes up, in fact, let's go ahead and draw a graph of how it's going to react. Get this out of the way so we can draw the graph. So here is our scale. Our horizontal scale is frequency, and our vertical scale is reactance. So we have inductive reactance and capacitive reactance, and I'm going to draw the inductive reactance in blue. So at low frequencies, the inductor has very low reactance. It starts to look like a short circuit, so we start down here. But as our frequency goes up, our inductive reactance goes up. So there's our inductive reactance, and it is linear to frequency because we double the frequency, we double the inductive reactance. But on the other hand, the capacitor at low frequencies looks like an open circuit, so it has a very high capacitive reactance. And as that frequency goes up, the capacitive reactance goes down. So frequency goes up, inductive reactance goes up. Frequency goes up, capacitive reactance goes down. So we're interested in this area here because over here it looks pretty much like a short circuit, and over here it looks pretty much like a short circuit, although we can make use of that, and I'll talk about that down the road. But we're mostly interested in what's going to happen here, where we have some reactance happening. So let's take a look at what goes on in this region, which may be a little unintuitive, because if we look at this, we say, well, let's see, I have my inductive reactance and my capacitive reactance. How do they work together? Well, don't forget that in our circuit, I'll draw a miniature version right up here. So we have a capacitor and an inductor, and in this case, since everything's in parallel, the voltage is going to be the same everywhere. So as the voltage goes up here, voltage goes up, voltage goes down, it's the same everywhere. So what's going to be different is going to be the current. Remember, the current in the capacitor is going to be 90 degrees ahead of the voltage, and the current through the inductor is going to be 90 degrees behind the voltage. Don't forget about Eli the Iceman. So the current's going to be ahead of the voltage in the capacitor, and the current's going to be behind the voltage in the inductor. So the current's ahead in the capacitor by 90 degrees, and the current's behind in the inductor by 90 degrees, and that means it's a total of 180 degrees. So the current is 180 degrees out of phase between the two components here. So that means that these currents are not adding up directly, and they're not subtracting from each other either because they're in parallel. And I'm going to get into the math on that later, but just real quickly, quick peek. Remember that our total impedance is going to be our impedance of our capacitor times our impedance of our inductor over the impedance of the capacitor plus the impedance of the inductor, and that gets complicated, but when we do the math we can get the actual numbers, but I'm going to show just graphically what's going to happen with the impedance of the circuit. So let's get this out of the way. Let's get that out of the way too. So in green I'm going to show the total impedance, and of course the total impedance is going to be 0 at DC and 0 at very high frequencies, but as our frequency goes up our impedance is going to rise. And it's going to follow a curve that looks something like this. And what's going to happen is at the frequency where our capacitive reactance crosses our inductive reactance, this is going to appear to go to infinity. And then it'll come back down something like that. And that's one thing I have a real hard time explaining from a conceptual point of view, is why this goes up so high, why it goes up to infinity. Why do I have an infinite impedance when I have two components in parallel where, well, when one's a high impedance, the other one's going to be low and vice versa? How is that going to become an infinite impedance? And like I said, I haven't found a way to illustrate that conceptually, but I can show mathematically that it will happen. And of course, in the real world, we look at practical circuits and we see that that does appear to happen. So that is what happens to our circuit if we have no resistance in there, as I've illustrated the circuit so far. However, in the real world, we're going to have some resistance in there. Let's see how that works. So let me draw this again. There's our inductor. There's our capacitor. And the inductor is going to have resistance, and the resistance of that inductor manifests itself in parallel with the inductance. So what's going to happen there? When this circuit looks like an infinite impedance, we're going to have some resistance that is less than infinity. And so what happens when you put a low resistance in parallel with a high resistance? Our total resistance is less than the lower resistor. So this is going to give us an impedance of less than infinity. And so in reality, this does something a little different, and that's going to be that it gives us a curve that looks more like that. So that is the impedance curve of a capacitor and an inductor in parallel. Under practical application, we see that the impedance goes up and up and up and up, and then it's going to peak, and this peak is going to be what? It's going to be equal to our resistance. So whatever our inductive reactance is or our capacitive reactance is, the maximum we're going to get is going to be equal to that resistor. So now we've determined that we have a curve like this at low frequencies, very low impedance, at high frequencies, very low impedance. At the frequency where our inductive reactance crosses our capacitive reactance, we're going to have our maximum impedance, and that maximum impedance will be equal to the resistance. Now there's a name for this. I'm going to go ahead and throw it out now, although I'm not going to use it practically for a little while, I don't think, but that's called the resonant frequency. So the resonant frequency, or frequency of resonance, is where our X sub L equals our X sub C. So that's by definition what the resonant frequency is. And we can calculate that out with a simple formula. Our resonant frequency is equal to 1 over 2 pi times the square root of LC. Now I have a previous video where I show where this formula comes from, because you look at that and say, where's the square root stuff come in? Because we have our X sub L equals 2 pi FL, and X sub C equals 1 over 2 pi FC. And well, How does that turn into that? Well, I have another video, which I'll link in the description below, where I show how this turns into that, but I'm not going to explain that just now. So let's just get that out of the way. So once again, the frequency where our capacitive reactance is equal to our inductive reactance is our resonant frequency, and that's the frequency where we have our maximum impedance, and that maximum impedance is equal to the resistance of the circuit. And if I add more resistance to the circuit by an external resistor, that's going to be in parallel with that resistor, so it's going to be less resistance, and so that will bring our maximum impedance down. And what it will do is basically push that top down. The rest of the curve doesn't change much, but it's going to push that top down. So let me just redraw it here as it would appear. So it's going to go up, and then it's just going to heel over and go back down. So I add more resistance in parallel, my maximum impedance gets lower and is still equal to whatever my total resistance is. Once again, remembering that these are in parallel, so adding resistance decreases the resistance because they're in parallel, so that brings down the maximum impedance. And it rounds off my curve. And there's a name for the shape of this curve. That's called the Q, which comes from the word quality. And if we have a good sharp peak, the higher this goes and the more sharp those lines are, we have a higher Q. And when we have a lower peak with less vertical lines, we have a lower Q. Now let's take a look at the voltage across this circuit as we go across the different frequencies. Well, the voltage is going to be directly proportional to the impedance. So at low frequencies, the voltage across the circuit, so we put a voltmeter across here, we're going to see that voltage at low frequencies being low, and that voltage is going to get higher at higher frequencies. It's going to peak at the resonant frequency, and then that voltage will go down, and at high frequencies, the voltage is down low again. Could that be useful? Could we use a circuit where the voltages at a certain frequency are high, but the voltages at lower and higher frequencies are lower? It could be a circuit that only reacts to a certain range of frequencies. And we could manipulate the Q of the circuit. If we want to respond to a wide range of frequencies, we'd want a low Q. If we want to respond to a narrow range of frequencies, we'd have a high Q. So that's what would happen to the voltage as we sweep across these frequencies. But another thing is, what about the current? So let's take a look at the current through the circuit. So at low frequencies, our current is going to be pretty high because it has a low impedance. But as our frequency goes up, the current is going to be sort of a flipped image of the voltage. So if I have a high Q, I'm going to have a current that goes down low, and then it's going to go back up. And if I have a low Q, the current is going to go something more like this. And so the current kind of does opposite of the voltage. It starts high and goes low and then goes back high again. And so we can manipulate how this circuit works as a frequency filter by whether we're interested in the current or the voltage. Let me illustrate what I mean. I don't want to get into filters just yet, but that's one of the things we can do with this circuit. So let's take a quick look at that circuit as a filter. If we have the parallel circuit such that we are interested in the voltage across it, in other words, the circuit is in parallel with our signal, so here's our ground, and here's our signal coming in. Well, what we're going to get is a band pass filter. At low frequencies, we'll get a low voltage, so not much comes through. At high frequencies, we get a low voltage, so not much comes through. But near the resonant frequency, we're going to get a high voltage, so we will see a filter that gives us a profile that looks like that. It doesn't respond to low frequencies, doesn't respond to high frequencies, but does respond to the band that's near the resonant frequency. But what's going to happen if we flip this sideways? Now we have our signal coming in, and we go to our circuit. Now what's going to happen? We have a ground somewhere else. Here's our ground coming in. Here's our ground going out. Maybe not the best way to illustrate it, but it'll have to do. So what's going to happen? At low frequencies, we're not going to get much current. Let me put a load here to illustrate what's going to happen, because we're interested in the voltage across that load now, because that's what's going to transfer into the next stage or whatever. So at low frequencies, once again, this acts like a low impedance, so we get high current. So low frequencies, let me draw a little quick graph here. Low frequencies, high current. High current is going to cause a high voltage across here, so we get a high voltage, but as the frequencies go up, that voltage is going to go down. And then at the resonant frequency, it's going to be a minimum, and then as frequency goes up, that's going to go up again. So let's illustrate those together. Let's have the circuit in parallel with the signal. With our voltmeter out here. And we'll have the circuit in series with the signal, with a load to give us a voltage, and then the voltmeter across the load. So here we are going to get a voltage that goes up and then back down. So we passed the band of frequencies near the resonant frequency, and we have a band pass filter. But in this arrangement, we have high voltage at low frequencies. It goes down and then back up. So the frequencies near the resonant frequency are rejected. We have a response at low frequencies, a response at high frequencies, but no response at the frequencies near the resonant frequency. So that band of frequencies is rejected, so we have a band reject filter. So that's an illustration of how the parallel circuit acts as a filter. And one more thing I want to say before I move on and conclude this first video about this is what happens at the resonant frequency. So let's draw that circuit again. And what I'm going to do is hit this with a square wave. And I'm going to put a high resistance between the square wave generator and the circuit for isolation. Without this resistor, we have a parallel circuit, so the voltage here will be the same as the voltage there, so this won't work, but this isolates it. And what's going to happen is when that square wave comes in, if we look at this on an oscilloscope, we'll see the voltage suddenly go up, and then it does that. And then when the square wave reverses polarity, we see the same thing happen again. We see a little bit of a ring, and the ring is at that resonant frequency. So this circuit responds by, we call it ringing, I don't know of a better thing to call it, of an oscillation that damps out quickly. That oscillation is dissipated as heat in the resistance of the coil, so it doesn't last very long. But we do get this oscillation at that frequency. In fact, I've heard many years ago that they took a circuit like this and got it oscillating like that in liquid nitrogen, and years later that was still going on because it didn't damp out, because it wasn't dissipating heat in the resistor. So it just keeps on going. So that's what happens to this circuit at the resonant frequency, is that we get this oscillation. And the reason it's doing that is, if we look at a moment in time, let's just pick a particular moment in time. Let's get this out of the way just to simplify the illustration. Let's say at the moment in time we have, let's say 1 volt across this capacitor. Well, this inductor is going to look like a short circuit, so this capacitor is going to discharge through the inductor. And what's going to happen as it discharges, it's going to build a magnetic field, and it's going to start storing energy in that magnetic field. And at the same time, this capacitor is discharging, so that voltage is going down as the current going through the inductor stores energy in that magnetic field. And eventually this is going to be 0 volts. So we've got our maximum current We've got our maximum magnetic field around the inductor, but we lose our energy and the capacitor. It eventually discharges. So we have a situation where we have no voltage across the capacitor and maximum magnetic field around the inductor. So what's that magnetic field going to do? It's going to start collapsing. And when it collapses, of course, it's going to continue pushing this current around the circuit. So what's going to happen? This capacitor is going to start charging the opposite direction. So before we had, what did we have? We had 1 volt. And I should have said this before, but let's say it was positive to negative, conventional current going that way. Now we've got 0 volts, but the current's being pushed by the collapsing magnetic field. And then we get the capacitor charging to the opposite polarity. And eventually that magnetic field collapses completely. It's no longer there. And so we have nothing pushing the current anymore, so the current is gone, but now that capacitor is charged to, let's assume that everything's perfect, we didn't lose any energy, that capacitor is now charged to 1 volt in the opposite direction. Let's go ahead and draw what just happened. So the voltage across the capacitor was 1 volt, and then it went down to negative 1 volt. But now what's going to happen is this capacitor is now fully charged. This looks like a short circuit, so it's going to start discharging in the opposite direction. So that's going to discharge. The voltage is going to go down. As that voltage goes down, we're building more and more magnetic field of the opposite polarity around the coil. So eventually this gets back to 0 volts. There we are there. But now we have the maximum magnetic field again. That magnetic field is going to collapse, continuing to push the current around the circuit. And so that's going to charge the capacitor. The capacitor is going to charge back up to 1 volt, positive to negative. And when it gets up there, the magnetic field will now have completely collapsed and the current will have stopped. And now we're back here again. So what's going to happen? We've just done 1 full cycle. This is going to now start discharging again, build the magnetic field, and that's going to drop this back down. The magnetic field is going to collapse, pushing the current the other way, and it's just going to go over and over again. So the energy is going to go back and forth from one side of the capacitor to the other, and the magnetic field around the inductor, out of phase with that, is going to build and collapse, reverse polarity, build and collapse, and we get a voltage across there that makes this sine wave. So that's what this circuit does at its resonant frequency, and that's why we call it a resonant circuit, because it resonates at that resonant frequency. Another name for this circuit is a tank circuit because it stores energy in like a tank, I guess. But if you hear someone talk about a tank circuit, they're talking about a inductor and a capacitor in parallel, or a resonant circuit that's going to act such as I've shown. So a quick review. A resonant circuit, which is what I tend to want to call it. I've been trying not to say resonant circuit until I explained resonance. Now I can say it. A resonant circuit consists of an inductor in parallel with a capacitor. And if we put that across a sine wave source, we will find that at low frequencies, that our inductive reactance starts low and goes high. Our capacitive reactors are inductive reactance. Our capacitive reactance starts high and goes low. And there's going to be a frequency where they are the same, and that's called the resonant frequency. So where the inductive reactance and capacitive reactance are equal, we call that the resonant frequency. The way this is going to react to our voltages is at low frequencies, we're going to get a low voltage across it that's going to climb and climb and climb. At the resonant frequency, that's going to want to go to infinity and then come back down as the frequency goes up. But in reality, there's going to be resistance in the circuit, and any resistance is going to bring down the impedance, and so that's going to lower that down. The maximum impedance will be the resistance. So if this has, I'll just draw it in parallel here, if that has 100 ohms of resistance, that's going to be our maximum impedance. And if that resistance goes down, that's going to bring that line down, and our impedance will max out at that line. The more resistance we have, the sharper the peak. The less resistance we have, the lower the peak. And The sharpness of this peak is called the Q of the circuit. So a sharp peak has a high Q and a less sharp peak has a low Q. If we're using this as a filter, if we have a high Q, we're operating on a narrow range of frequencies. And depending on how we arrange the circuit, if we put it across our signal, we get a band pass filter. If we put it in series with the signal, we get a band reject filter. And that band that's passed or rejected depends on the Q. So a high Q has a narrow band, a low Q has a wide band. So using it as a filter, we can manipulate the Q to see how wide of a band of frequencies we want to filter. And at that resonant frequency, this circuit wants to, quote, ring. It wants to resonate. So if we put energy into it, and like I said, if we turn this into a square wave to make that dramatic, put in some resistance to isolate it, lots of resistance, because if we don't put the resistance there, the voltage here is the same as the voltage there, so it will not ring, it'll be all damped out. But we put some resistance there and hit this with a voltage, it is going to transfer energy back and forth across that capacitor, so the voltage goes positive to negative, swings around negative to positive, and the magnetic field around the inductor builds and collapses, reverses polarity, builds and collapses, and that energy trades back and forth, creating a sine wave at the resonant frequency. So those are the basics of a circuit that has an inductor and a capacitor in parallel. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.